Hello and welcome. Today we're going to be looking at static fluids acting on a wall. So the forces that static fluids exert on surfaces which are submerged in those fluids. Here are some examples of surfaces that we see being exerted or having forces exerted on them by fluids in everyday life. There's a dam on the left-hand side, a hot air balloon in the centre, and a shipping container, or a ship with shipping containers on it, on the right-hand side. So on the left, clearly, the surfaces at the bottom of the dam or throughout that dam have got fluids acting on them. So we're going to be learning about what forces are exerted on those surfaces, so that we know how to construct such a structure, so that we don't see failures and it can deal with the forces exerted on it. On the right, in the centre, we have a buoyant object, a hot air balloon. So we're going to be looking at the buoyancy forces which are generated by such an object being submerged in a fluid. So there, clearly, we've got one fluid, helium or whatever it is, or hot air, and that is surrounded by another fluid, and therefore those fluids have different densities and so on, and we can calculate the buoyant forces which are generated accordingly. On the right hand side, we have a shipping container, or a ship with shipping containers on it. So we've got a stable floating body. We'll be looking at the forces, the buoyant forces which are generated from that body, and also how can we ensure that that remains stable. So if we look at the things that we're going to be looking at today, we're going to be looking at, starting off by looking at the variation of pressure with depth. So as you go deeper in a fluid, why the pressure increases. We'll then move on and we'll have a look at the forces which are exerted on a submerged surface. In order to do that, we need to understand not only the forces, but also where those forces are applied on those surfaces. So we need to understand the centre of pressure. So we'll be looking at how to find the centre of pressure. We will also then move on and we'll be looking at forces on submerged curved surfaces. So here we're looking at flat surfaces, planar surfaces. We'll then look at curved surfaces, and I want us to understand how we would calculate forces on such a surface. And then finally, we'll have a look at buoyancy and stability. So how we can calculate how buoyant an object is, and whether or not that object is stable or not. Okay, so let's now understand why pressure varies as you go deeper. So here we have a pink fluid represented in this image here. The forces on the grey wall are close to zero near the top, and then they increase as we get deeper and deeper. So on the right hand side we have a piece of fluid, and we know the pressure at this depth is a certain pressure, P1. As we go deeper, delta Z, so as we move down in the Z direction, P2 increases. So let's consider how we would calculate what that pressure increase is. Let's look at it in 2 dimensions. So let's not consider the third dimension. So the third dimension would be the Y direction into and out of the page. Let's neglect that for the time being. We're going to look at this purely in 2 dimensions. So we know pressure equals force over area. So therefore force is pressure times by area. So if this is sat in equilibrium, this piece of fluid, the upwards forces minus the downwards forces, that's the sum of my forces, that's equal to mass times by acceleration. So the upwards forces, what are the upwards forces? Well, it's pressure times by area. P2 is my pressure, and the area, delta X, delta Y, but we're going to assume delta Y is unitless, is of unit thickness, so therefore we neglect that. So actually it's just P2 times by delta x. That is the upwards force minus the downwards force. The downwards force would be P1 times by delta x times by delta y, if we're neglecting that thickness. It's just P1 times by delta x. So therefore the sum of the forces would be P2 delta x minus P1 delta x. That's equal to mass times by acceleration. So what's the mass of this fluid? Well, the mass of this fluid would be the density times by the volume. The density rho, there's density rho, and the volume would be delta x, delta z. If we're looking at it just in 2 dimensions, actually it's just the area, delta x, delta z. So there's delta x, delta z. The acceleration, well, acceleration, let's take g, acceleration, this is in static equilibrium, so acceleration due to gravity is sat at 1g. So rho, delta x, delta z, that's my mass, g, that's my acceleration. So if we then divide all of these terms by delta x, we end up with P2 minus P1 on this side, so that's delta P. We divide through by delta x on this side, we end up with rho g delta z, rho g delta z. So change in pressure equals rho g delta z. Ordinarily, what you would see actually is change in pressure equals rho g h. So the height of the fluid, the height of the change, as you're moving down through the fluid, what is that height? That height is delta z in this diagram here. So change in pressure equals rho g h. That's how we can calculate the variation of pressure with depth. Okay, so we understand how pressure changes with depth. Now let's see how we can calculate the force exerted on a submerged surface. So pressure equals rho gh. So on this diagram here, we have a submerged surface, this surface here. So we've got this flat surface here, submerged in this pink fluid. It is submerged a distance here. We've marked this in the y direction. So the y-axis runs along the length of the object. Height is the depth of the fluid. So this surface is orientated. So theta separates this horizontal plane to the plane that the object is sat in. So this point here, this surface here, this small part of this surface, let's call this dA. That is a distance, a height, h, below the surface, and h, therefore, would be y sine theta. Y sine theta tells me my position, my height of this small surface here. We've also marked on this diagram this point here, that's called the centroid, so the centre of area of the object. And we've also marked on there Cp, the centre of pressure of the object. And because pressure increases as we get deeper, we would expect Cp to be lower than C, centre of area. So it's in the centre of my object there. Cp, centre of pressure, is going to be a little bit lower. Okay, so my pressure equals P0. P0 would be my atmospheric pressure, it's on top of my fluid. So my total pressure at this point down here on this area would be P0 plus rho gh. Rho gh, we've just said, if this plate is orientated such that it's inclined at some angle theta, h would be y sine theta. So my total pressure equals my atmospheric pressure plus rho g y sine theta. Okay, so there's my pressure. Okay, so now let's calculate what is the force on this plate? Well, my force is going to be the sum of my pressures over these areas. So I'm going to have to integrate this plate. I've got lots of these small areas. I'm going to add all those together. I'm going to integrate it over the complete area. So my force equals the integral over the area of pressure. Okay, now we've just said that pressure equals P0 plus rho g y sine theta. So if I put this equation here into this equation here, I'm going to end up with this equation here. So the sum, my forces are equal to my integral over the area of P0 plus rho g y sine theta dA. Okay, so if I integrate my atmospheric pressure with respect to area, we're going to end up with P0A. Okay, so that's where this term comes from. Rho g sine theta. Clearly, that's not a function of y. Rho g sine theta. Rho g sine theta. Therefore, I can bring that outside of my integral sign. So we're going to integrate over my area of y dA. Now, the integral over the area of y dA, that is known as the first moment of area. Okay, and the first moment of area would be this area times by the distance to the centroid. And I've called that YC in this diagram. So YC times by A, that's the first moment of area. Okay, so let's rewrite this equation. But instead of writing the integral over the area of y, that's my first moment of area, I'm just going to write YCA, my distance to the centroid times by the area. So I've got FR plus P0A plus rho g sine theta YCA, where YC is my distance to my centroid. Clearly, I can factorise that. I've got A in this term here, I've got A in this term here, so I can put A outside of those brackets, so I end up with P0 plus rho g YC sine theta times by A, and there, instead of writing YC sine theta, I've written HC, where HC is the vertical distance to the centroid. So there's my centroid. The distance to my centroid is YC. I'll write that in terms of H. Clearly, I've called that HC, the vertical distance to the centroid. So my force equals this pressure times by the area. Now this pressure here, P0 is my atmospheric pressure plus rho g HC. So that is the pressure at the centroid, because it's the height that the centroid is below the surface of the fluid. So there I've rewritten it, and I've written it as PC. So PC is the pressure at the centroid. So FR equals PC times by my area. So the total force on this submerged surface is the pressure at the centroid times by the area of the plate. Okay, that's how we'd go about calculating the force on the submerged surface. So the force on the surface below the fluid is simply the pressure at the centroid times by the area of the plate. On the previous slide, we calculated how to work out what the total force was on a plate submerged in a fluid. What we want to do now is to understand where that force acts on that plate. So this diagram on the right hand side is representing our total force on our plate, which we've calculated as the pressure at the centroid times by the area of that plate. And we're now assuming that that total force acts at this location here, which is called the center of pressure. And that is located a distance yp from the origin. So on the previous slide, we were talking about the centroid and we said that was a distance yc from the origin. We have now got a representation of the total force, and that is located here at the centre of pressure, which is a distance yp from the origin. So if we were to consider the total moment on this plate, the total moment being the force times by the distance to the centre of pressure, that's going to be equal to the sum of the pressures on each small element summed together and then times by the distance to those small elements. So the integral over the area of yp dA. Now, we saw on the previous slide that P was equal to the atmospheric pressure plus rho g y sine theta. So if we now put that into this equation here, we end up with yp times by fr, so our moment, being equal to the integral of y times by the atmospheric pressure plus rho g y sine theta dA. Now, we saw on the previous slide that the integral of y dA is called our first moment of area, and that's equal to yCA. We also know that the integral of the area of y squared dA is the second moment of area, around the origin, and that's equal to Ixx, comma 0, or comma O, shall I say, comma the origin. So the second moment of area around the x-axis relative to the origin. We also know from the parallel access theorem that if we want to calculate the second moment of area around the origin, or around a vector which is parallel to our centroid, we just calculate the second moment of area of the centroid and we add y squared a. So that will give me the second moment of area around a distance from the centroid. So second moment of area of the centroid plus y squared a equals the second moment of area around our origin. So therefore, if we plug that into there, rearrange it, we can calculate this distance yp. What is this distance to the centre of pressure? Okay, and if we say P is 0, or close to 0, the atmospheric pressure, the P0 is close to 0, that term disappears and we end up simply with Ixx around the centroid divided by yCA plus yC equals yp. So we can calculate where the centre of pressure is. Okay, so let's have a look at that in a bit more detail. So let's look at that in a bit more detail. Let's try and understand how we can get from this equation here, so this is our distance to our centre of pressure times by the total force on the plate, how we can use that to understand how we can calculate what yp is, what the distance is to that centre of pressure. So we're going to start with this. Our distance to the centre of pressure times by the total force on the plate, and that's equal to the integral of A of y times by P dA. Now, we've said before that P, our total pressure, is our atmospheric pressure plus rho g h, or rho g y sine theta. So let's plug this equation here into here. We end up with this equation here. So our distance to our centre of pressure times by the total force is equal to the integral over the area of y times by this bracket, and this bracket represents the total pressure. That is this equation here. So we're going to integrate that term there. So we've got two terms there actually. We've got P0 and we've got rho g y sine theta. There's two terms in that bracket. So let's expand that. And so instead of integrating this entire bracket, let's integrate this first term. Let's integrate this second term. So we end up with two terms there. So that first term, P0, times by the integral of y dA. That's this term here. This second term, let's change our colours. That second term there, rho g y sine theta times by y times by the integrated over the area is going to be equal to rho g y squared y times by y, so y squared sine theta dA. So if we then take those terms, P0 is clearly not a function of A, so we can move that outside of the integral sign. So we end up with P0 times by the integral of y dA. The integral of y dA, we've said before, that is known as our first moment of area. So this here is our first moment of area. Okay, and we're going to plug that into the equation here. Okay, this second term, we've got rho g sine theta. Clearly that's not a function of A, so we can move that outside of our integral sign. So we end up with rho g sine theta times by the integral of A y squared dA. And this term here, integral of y squared dA with respect to A, that is known as our second moment of area. Okay, and we're going to plug that into here. Now, that is the second moment of area around the origin. Okay, and we'll come on to why that's important in a minute. Okay, so let's take this equation here. Now this is equal to yp fr. So the distance to the centre of pressure times by the total force is equal to this term here, this equation here. Let's now plug in our first moment of area and our second moment of area. So ypfr is equal to P0. Instead of writing that lot, I'm going to write YCA, the distance to the centroid times by the area, the first moment of area, plus rho g sine theta, and then instead of writing that, the integral of y squared with respect to the area, that's our second moment of area around the origin, so I'm going to put that in there, second moment of area around the origin. So that's where we get to that. So we've now got to that equation there. Now, we also know from parallel access theorem, if we want to know the second moment of area of an object around the origin, we take the second moment of area of an object around its centroid and then just add y squared a. So the distance from that origin squared times by the area. So we can now put that, this equation here, we can now put that into there. And that's what we're doing here. So we've now got ypfr equals P0 YCA plus rho g sine theta, and then instead of writing Ixx around the origin, we've got Ixx around the centroid plus y squared Ca. So there's our parallel, that comes from our parallel access theorem. If we then take that and we manipulate that equation slightly so we can expand those terms, so we've got three terms there now. So this first term, this second term is here, look. That's multiplied by Ixx on the centroid. Then the third term is going to be rho g sine theta times by this, y squared a. So if we expand those brackets, we end up with 3 terms. So my first term is this one, rho g, P0 yc times by the area. The second term then is going to be this one here, rho g sine theta ixx times by the centroid. And then the third term is going to be this one here. So rho g sine theta y squared a. If we then rearrange that, factorise it, we can see that this green term here is multiplied by yc. We can also see that this term here, this blue term here, is also multiplied by yc. So that green term is now there, look, and that blue term is now here. I've simply factorised those and taken yc out of both of those equations. Okay, so yc times by that is going to give you the green term, yc times by that is going to give you the blue term, and then the red term shown at the end here, we've got rho g sine theta ixx around the centroid. Now this here, P0a plus rho g sine theta yca, hopefully that looks familiar to you, because that actually is FR. Right, so there, P0a plus rho g sine theta yca, we've shown before that that is the total force the next stage. Okay, so let me zoom out a little bit. So we've taken this equation here. Instead of writing this bracket here, I've just put in FR. Here, look. Plus rho g sine theta ixx around the centroid. So that's how we would then get to this location here, to this equation here. If we then divide by FR disappears here, so we end up with YP. FR is going to disappear here, so we end up with YC. And if we then divide by FR, if we divide this by FR, remember this is FR here, we've then divided by FR, so that there is sat underneath that equation, look. P0a plus rho g sine theta yca. If we then divide top and bottom of the fraction by rho g sine theta, we end up with this. So we're going to, looking at our fraction, we're going to divide through by, so this term here, rho g sine theta, that cancels with that, rho g sine theta, and then we're also going to divide this last term here by rho g sine theta. We end up with this. So we've got yc plus ixx around the centroid on the top of the fraction here, and then this term here is now here, look. So that's yc times by a, yc times by a, and then here you've got P0a divided by rho g sine theta, rho g sine theta. If we then factorise that, so these bottom two terms here have both got a in, look. So if we bring a outside of our brackets, we're going to end up with that equation there. Now, that equation, if we look back here, that's this equation here. Okay, so that's going to enable us to calculate YP. Where is YP? YP, remember, was our distance to our centre of pressure, and that's equal to the distance to the centre to the centroid plus, the second moment of area of the shape around the centroid. And we know this information here. We can work out what YP is, where YP is, what are the distances to the centre of pressure. Now, generally, the pressure under the water is significantly greater than the atmospheric pressure. The atmospheric pressure is pretty close to zero. So this term here, if P0 is close to zero, that term there is going to disappear. So we end up with this, YP equals YC plus IXX around the centroid divided by YCA. Now that there is this equation here. So what does that actually tell me? If we want to calculate where the centre of pressure is, we just take the distance to the centroid and we add the second moment of area relative to the centroid and divide that by the distance to the centroid times by the area. And we can calculate quite easily where that centre of pressure is. Okay, so that's how we'd go about finding out where, not only on the previous slide we saw the magnitude of that force, we can now calculate where that would act, where the centre of pressure is acting on that plate which is submerged in that fluid. So we saw on the previous slides how we can calculate the force acting on a plate, and in order to calculate that, we need to know where the centroid is. We also saw how we can calculate where the centre of pressure is, where that force is going to be acting on that plate. And in order to do that, we need to know the second moment of area of the plate around the centroid. So what we're looking at here are some basic shapes, and we can understand the position of the centroids. So that's what these locations are showing here. We've got the position of the centroid for each of these shapes. We've also got the second moment of area for each of those shapes. So for a rectangle, C would clearly be, the centroid would clearly be in the centre. So this is B meters deep, B over 2 to the centroid, B over 2 to the centroid. If it's A meters wide, we'd have A over 2 to the centroid and A over 2 to the centroid. If we want to work out the second moment of area, well, that's AB cubed over 12. AB cubed over 12 for our rectangle. We can also see the information there for a circle, an ellipse, triangle, a semicircle, and a semi-ellipse. So these are all standard relationships that we might use to understand the magnitude of the forces on plates which are submerged in a fluid, and also the position of those forces of plates which are submerged in those fluids. On the previous slide we saw some standard relationships for finding the centre of pressure and the magnitude of the forces on flat submerged surfaces. However, a lot of the time surfaces which are submerged in fluids are not flat, they're actually curved surfaces, such as the image is showing here of the Hoover Dam. Clearly those surfaces are curved. So what we need to do is we need to understand how we can calculate the forces acting on curved surfaces. Now that's very easy to do. If we consider a curved surface under some fluid, such as we're seeing here, so this surface here, AC, is clearly a curved surface. If we know this is set in equilibrium, we can just simply create a vertical plane there, BC, and a horizontal plane there, AB. And we know if this is set in equilibrium, that FH, the horizontal forces on this curved surface, are the same as the horizontal forces on this flat surface. So if we calculate Fx, the force on that flat surface, that's going to be the same as the horizontal component on the curved surface. So Fh, the horizontal force, is equal to Fx. We can also resolve it vertically. We know that the vertical forces on this curved surface are going to be the same as the vertical forces on this flat surface, AB. So this force on this curved surface is going to be the same as the force on this flat surface. However, in addition to that, we've got this block of fluid, this fluid block, which is sat on top of there. So not only have we got the force acting on this flat surface, but we also need to consider the weight of this fluid, which is also sat on top of that curved surface. So that's hence we end up with that relationship there, that our vertical forces on our curved surface are equal to the vertical forces on this plane AB plus the weight of the fluid block sat on top of our curved surface. So we can calculate the two components, the vertical component and the horizontal component sat on top of our curved surface. Now what we might also want to do is to calculate the orientation of that vector acting on that curved surface. And in order to do that, we can simply use a little bit of Pythagoras. If we take the horizontal force and square it, and look at the vertical force and square it, and then square root the sum of those two forces, clearly that's going to give me the magnitude of the force acting on that curved surface. And if we want to understand the orientation of that force, we can just do a little bit of Pythagoras, and we know that tan alpha equals the vertical force divided by the horizontal force. So if we need to calculate the forces on our curved surface, we can just consider these two flat surfaces and just look at the forces on those, plus take into account the weight of the liquid between those two flat surfaces and our curved surface, and then we can work out the magnitude of the force on the curved surface by using Pythagoras, and the angle of the vector for the force on the curved surface using some trigonometry. Okay, so we now understand how to calculate the forces on a flat surface submerged in fluids, and we also know how we can use that to calculate the forces on a curved surface submerged in fluids. So what we can look at now is something called buoyancy. And what I want to understand is, if you've got an object in a fluid, what upwards forces are exerted on that object? Why is there an upwards force? What is that upwards force? Okay, so here we've got an example of that. We've got an object immersed in a fluid, and clearly that is a buoyant object, this balloon here. So how do we calculate what the magnitude is of that buoyant force? Okay, so let's consider this diagram here on the right hand side. Here we've got an object, this flat plate, inside this fluid. It's at a distance s below the surface of the fluid. We've got a height h, so the thickness of this plate, and the area of this plate is a, and we can calculate what is the total buoyant force on this plate. Now, we saw earlier, as we go deeper, the hydrostatic forces, hydrostatic pressure increases. So therefore, the pressure on top of the plate is going to be smaller than the pressure underneath the plate. Now, if we know the area of the plate and we know the pressures on the top surface and on the bottom surface, we can calculate the forces on the top surface and on the bottom surface. So the buoyant force is equal to the force on the bottom minus the force on the top. We would expect the force on the bottom to be greater because the pressure is greater. So the force on the bottom is going to be our greater force, and we need to subtract the force on the top. And the total, the difference between those two forces is going to be the buoyant force. So the force on the bottom of the plate is our pressure times by our area. Now, the pressure on the bottom of the plate is given by rho g h, rho being the density of the fluid, g being gravity, and h being the distance from the top surface. So that's rho of the fluid, g, and actually it's not just h, it's s meters below the surface, and then there's h there, the distance, the height, the thickness of the plate. So there's our pressure, rho gh, times by the area. So therefore that's the force on the bottom of the plate. Now the force on the top of the plate is similar. Rho gh is our pressure. This time actually h, it's not h, it's s, isn't it? It's rho g s. That's the pressure on the top of the plate, and the area is the same. So we've got a there. Okay. So our buoyant force is rho g s times by a, rho g h times by a, minus rho g s times by a. So clearly the force or rho g sa subtracts or cancels there. So we end up with rho g h a. So the density of the fluid times by gravity times by HA, HA being the volume of the object. So our buoyant force is given by density of the fluid times by gravity times by the volume of the object, which is displacing that fluid. So what does that actually mean? What does that actually tell us? Well, there's the conclusion that we can draw from that. The buoyancy force is equal to the weight of the fluid displaced by the object in that fluid. Where does it act? It acts through the centroid. So we were talking earlier about what a centroid is, and we looked at some basic shapes and how to calculate the centroid for certain shapes. We know how to calculate the centroid for various objects, and the buoyant force acts through the centroid of that object, and the magnitude of that buoyant force is simply given by the weight of the fluid displaced by that object within that fluid. On the previous slide, we saw if an object is fully submerged in a fluid, how we can calculate what that buoyancy force is, the force which the fluid would exert on that object. However, we don't always have objects which are fully submerged. And in this image here, we can see clearly an object which is partially submerged in that fluid. That ship with those containers on is clearly partially submerged in that fluid. So what is also important is to understand how stable those objects are when that happens. So we need to think a little bit about stability for an object in a fluid. So to begin with, if we have a look at these images up here we've got a spherical object which is fully submerged in a fluid. And as long as G, the centre of gravity, is below B, the buoyancy force, the position where that buoyancy force is being applied, we have an object which is stable. So here, this object, we've got this spherical object, we've got some weight added to that sphere. That weight is sat at the bottom, so that's going to lower our centre of gravity, so that's below our buoyancy force. So this object is stable. If the centre of gravity and where the buoyancy force is being applied is in the same location, it's neutrally stable. So here we've got an object which is neutrally stable, and what we mean by that is it's not stable, it's not unstable, it's right in the middle, it's neutrally stable. And conversely, this last image here we've got our sphere. The additional weight has been added at the top of the sphere, which is going to raise the centre of gravity. So the centre of gravity is now above where the buoyancy force is being applied, and this is unstable. Why is that unstable? Well, clearly there's going to be a restoring moment. Clearly that centre of gravity wants to come down below that buoyant, where that buoyancy force is being applied. So if we've got an object which is fully submerged in a fluid, as long as G is lower than B, we have a stable object. Okay, let's now consider this second case. What happens now if our object is not fully immersed in that fluid? Well, here we need to define something else. We need to define this this definition of M, our metacentre. And how is our metacentre defined? Well, if we take our centre of buoyancy, and we draw our vector up there where that crosses the axis where the centre of gravity is, that is defined as our metacentre. So as long as our metacentre is above our centre of gravity, such as in this image here, we've got a stable object. Okay. However, where we need to be concerned is where if that object were to tilt even further, such that the centre of gravity moves in this direction, the centre of buoyancy moves by a lesser amount, and if we were to draw that vector now, our metacentre is now below our centre of gravity. At that point, our ship or our object is unstable, and we're going to end up having an overturning moment. So in that situation, we would expect that object to capsize. We would have an unstable situation. So as long as our metacentre is above our centre of gravity, we've got a stable object. That ship is going to right itself. However, as soon as that centre of gravity moves too far, such that the metacentre is now beneath that centre of gravity, we've got an unstable object. Question number 1 describes a car which is involved in an accident, and that car ends up in the bottom of this lake, and I want you to understand, use the question to calculate the hydrostatic forces which would be applied on that surface. And actually in that question, what we're going to be assuming is that is the door can be assumed to be a flat, a planar surface under the water, and I want you to try and calculate what the force is on that door, where the central pressure is on that door, and whether or not you think the person would be able to get out of that car. The second question is all about forces on curved surfaces. So here we have an automatic gate, such that when the water in this lake gets to a certain height, the gate automatically opens, and the water is allowed to escape underneath this gate. So I want you to work out what the forces are on that gate, and therefore you can calculate what weight of object you need to resist that. And then the last question is all about buoyancy, and I want you to use this scenario to understand what tension you would have in this rope if this object were being held in air, and then it's lowered into the sea. It's used as a sea defence underwater construction project. So what would be the tension rope when you lift it in the air, and then when you lower it into the water, what would be the tension in the rope? So have a go at those questions, and what I will do is I will upload some solutions to those questions. I will upload these worked solutions to those questions. There's question number 1, look. Question number 2, and question number 3. Have a look at those questions, try those questions for yourself. I will upload the solutions to those questions. I will also upload a video of myself going through the solutions to those questions. So if you need some help looking at those and going through those, I will describe that with you. If you have any additional questions after that, of course, you can email me. What I will also upload is this PDF here, which I went through earlier, which shows the derivation of how to calculate the location of the centre of pressure, so that you have that so that you can work your way through that and check that you're happy with that. If you want to read further about any of the information which I've been talking about today, there's some sources for you to look at there, and a lot of the images and information that I've been presenting today have come from those sources. So please have a look at those. I would recommend you look at those in order to understand the subject further. What we've been through, looking at static forces on surfaces under the water,